Great. So welcome everybody. Thank you very much for joining us today. I'm Agnes Sodri. I'm a postdoc at Minerals to Metals. And the project that I will talk about today practically just started in February. It is a collaboration between the University of Queensland and the UCT. And it is about using stable isotopes to track acid rock drainage related processes at a South African colliery. And today we will only focus on sulfate as the contaminant and the sulfur isotopes. Our main goal with the project is to generate information that allows us to create more accurate characterization in order to minimize the potential impact of acid rock drainage on local natural water system. To achieve this, it is essential to understand the mechanisms taking place during acid rock drainage formation, to identify the source of various contaminants, as well as the process that control their mobility in the water. To fulfill these requirements, we will mainly use a stable isotope technique that is still not routinely used in ARD studies, especially in South Africa. And because of that, only little is known about how useful this technique could be in the South African acid rock drainage research. And also because of that, the study will be a benchmarking exercise that can provide reference data set for future isotope projects on the studied area. So as the project is in the very early stage, today I can share only very basic preliminary results. Here is the plot of ferrous iron and pH that represents the decreasing solubility of this iron with the increasing pH values. Whereas the behavior of sulfate against pH is not that straightforward. The lack of any trend on this second diagram can be the result of the contribution from multiple sulfur sources, and at the same time, it also can be the consequence of sulfate consumption by different secondary processes like bacterial sulfate reduction, secondary sulfate remobilization, or even precipitation. So in order to follow up the governing mechanisms behind these very variable sulfate concentrations, it is necessary to identify the sulfur sources and the processes that induce the transformation of this element in the mine water by measuring the sulfur isotopic composition of dissolved sulfate in mine water. So let's have a closer look at the possible sulfur sources on the area. First of all, we have the pyrite in the coal that is considered the main source of sulfate. But besides this, due to the weathering and the different mining activities, the saline pore water from the underlying Karoo sediments can be liberated, and it also can contribute to the sulfate in the groundwater and surface water bodies in the form of. In addition, as most of the land around the mining area is agricultural and most of the South African power stations are located in Mpumalanga, sulfate from fertilizers and atmospheric sulfur deposition also can contribute to the dissolved sulfate, as well as sulfur from coal combustions. To make it very simple, in the ideal case, the sulfur isotope composition of the dissolved sulfate should be closely identical to that of its main source, in this case, the pyrite, but different physicochemical and microbiological processes can override the original isotopic composition because those have the potential to fractionate the heavier and lighter isotopes from each other. And in this case, the degree of the fractionation should refer to the process that triggered the isotopic variation, and that will allow us to identify the controls on sulfate mobility in the mining environment. So according to our expectations, the findings of the project will not only allow us to create more accurate acid rock drainage characterization, but also can help us to identify the main reactive sites of the mining area. And these results will have the potential to inform the improvement of different geotechnical designs, water management, or water quality monitoring program that ultimately can improve the emission control strategies of the studied mine site. Thank you.
Cool. Thanks, Agnes. Let me try and get my screen on. Yes. Yes. Okay. All right. So kind of moving almost from that, Agnes was talking about water quality management on the mine site. I don't know why this slide keeps jumping, but anyway, I'm now moving on to maybe looking a little bit more at the water quantity side of things. My project aims to use one of potentially a number of frameworks for the assessment of water-related impacts on a mine site. But today I wanted to focus in on a small aspect of it that's not necessarily always considered so much. And this is about the variation, potential impact of variation in the context systems such as mine sites and mine operations, mineral processing operations. So of course, there's many things that are varying, and particularly when we think about climatic factors, these can have a very big influence on plant operation. And I want to show an example of how that kind of thing can play out. So I want us to imagine for a moment that you are the proud owner of a phosphate mine, and you have some ore processing facilities where the raw ore is crushed and floated into a valuable concentrate and also producing some waste material. Of course, the concentrate is then dried and shipped off to whoever wants to buy it, like fertilizer or whatever. And the waste material needs to be processed to remove a lot of water before it can be placed on a tailings facility. So at this tailings facility, of course, is where a lot of the interaction of the mine site with the outside world happens, where rainfall lands on the facility. There's a lot of evaporation taking place, and also potentially seepage to groundwater, depending on the geotechnical aspects around the tailings. So we also need to treat some of the water potentially, because either we need to manage the discharge quality of our water, or potentially the processing side of things requires a certain kind of water quality. So we can see how these different areas on the mine all kind of stick together. And certainly there's a loop going around where we recycle water, which can also influence things. In this particular case, the mine is not necessarily self-sufficient in terms of water. It needs to pull some groundwater to make up for losses. So assuming we know a little processes behave, we can try to model this and see how variation with time affects it. So the first part of that equation, as it were, is to try and understand the impact of rainfall and evaporation variation. So this kind of natural system behaves in a bit of a stochastic way, right? Because on some days you have rain, on other days you don't have rain. And of course, some months in dry seasons, for instance, will have no rain at all. You can kind of see this looking at the cumulative rain graph, but it's much clearer on the next slide, which I'll show you now. So that was just 1 year, of course, but we know that we can kind of make an assessment of how variation due to various climatic factors can play out over a number of years. So if we run a simulation for quite a large number of years, we can get a spread or a sort of probability cloud of the kinds of rainfall trajectories that we can expect, right? So each of these different lines represents a different potential year that we might have, ranging from a very high rainfall year, which might happen, to a very low rainfall year. But of course, on average, we seem to get more average years and fewer of these freak years. By the way, this is the sort of analysis or understanding which might have helped to understand the drought that happened in Cape Town. You know, in that particular case, you have a number of very low rainfall years happening consecutively, which of course has quite a low probability of occurring, but nevertheless, that probability is there. And understanding how these probabilities affect process outcomes is an important part of understanding risk. So if we move to, oh yeah, one other thing I wanted to mention here was how in this particular case, you can see very strongly the seasonality of the rainfall in this site, where in the beginning of the year, there's quite a bit of rainfall. In the middle of the year, almost no rainfall happens. And then at the end of the year, we start to see an uptick again in the wet season. So of course, this variation throughout the year has a big impact on the site. So if we see how this plays out in the context of some of our processes, we can look, for instance, at the tailings storage facility, which of course is very, it's influenced quite strongly by incident rainfall, you know, big events or lack of events. So if we assume that we start at the same volume of water at the beginning of the year and we let these different potential rainfall years play out, we similarly get a probability cloud of different outcomes of volume in the tailings. Now we can see that some years end up with almost twice the volume in the dam, and other years end up with no water. Both of these outcomes represent potential risks to the mine site. On the one hand, having too much water can cause, you know, stability issues and potentially result in the overtopping and subsequent spillage of the tailings dam, which can have major environmental consequences in many cases. And on the other hand, running out of water obviously creates a huge problem in terms of operational, because without water, the mine can no longer operate, and you may have to either source water from other places, but if that isn't enough, then you have to shut down your plant. So understanding these different potential outcomes and how potential interventions that you can make may affect the probabilities of these outcomes is obviously a really interesting and important aspect of the kinds of assessments that we want to do. And I just wanted to highlight sort of very visually how these different things can be identified. Yeah, that's me. Thanks. So next up is CK. Are you sorted?
Yep, I'm here. Let me just share my screen. Okay. There we go. So good afternoon, everyone. I'm Conchita, and I will be talking about my project, which is titled Characterizing the Potential Health Risks Associated with Coal Dust. So the theme for this presentation today will more or less be a high-level representation of how I view the usefulness of the project, as well as my approach to achieving our aim. So just to give a bit of context, dust in the mining environment can occur on various size scales, and what I mean by that is you have a dust plume created by an activity which can happen on a localized meter scale, and within that plume you have millimeter, micrometer, and nanometer sized particles that affect both the environment and occupational health. Also, being exposed to these kinds of dusts on mine puts you in close proximity to harmful metals. I also want to talk about the current monitoring controls, which only look at the intensity of exposure over a period, and this metric kind of assumes that there's equal toxicity between all dusts. So making this assumption neglects that there are inherent properties of different kinds of dusts which can impact how we perceive exposure risk. So recent studies have argued that the inherent risk of different kinds of dust needs to be characterized in order to aid in mitigation controls of preventable respiratory diseases. So specifically in my study, my overarching aim is to develop a risk characterization protocol for inhalable coal dust that takes into account the most influential physical and chemical characteristics of coal dust towards respiratory harm. So before I get into my approach of how I would do this, I just want to talk about the stakeholder landscape and the different technical domains that overlap at least from the perspective of my work, when we start to talk about health risk characterization of dust. So the first domain that I want to talk about is the air quality domain. And this can generally be viewed as work that's conducted around the generation activity, release, and exposure towards dust. The second domain is the immunology and particle toxicity domain, which generally works around the relationship, between exposure, dose, and effects. The third domain is that of individual particle analysis of particulate matter, which is that PM in brackets. And this involves the analysis of the physical and chemical components of dust, which is either conducted online, which is in real time, or offline, once the sample has been collected, the dust sample. So this blue block generally shows how risk definition is characterized in terms of exposure, and the health impacts are based on the assessment of cumulative exposure or exposure towards dust, which is generally represented as like the mass concentration of dust that you're breathing in. And like I said, this doesn't take into account the inherent properties of the dust itself that a person can be exposed to. So the perspective that we're taking in this project is to look into the potential generation of a complementary risk index, which looks at the characteristics of a material in relation to its potential to induce a toxic response. So how I envisage this is through a three-stage process, which are the three technical components of my work. And the first component looks at the characterization of various coal dust samples for their physical and chemical components, and then testing those samples in vitro to measure or get a measurement of their cellular response to dust dose. Then taking the information from that first stage and computing it to generate these indicator variables for risk characterization. And what I mean by that is to assess which physical and chemical characteristics have a influence on the toxic response measured. So once we have those indicator variables for risk, we'll take that to the third stage, which is categorizing which coals, categorizing the coals in a way of relative risk. So developing an understanding of the harm that different coals may possess depending on their physical and chemical characteristics, and that would be done by using weighting and scoring algorithms. So ultimately, what I would envisage this project to output is a new data set of particle characteristics which are relevant to respiratory harm and can potentially be considered in future mitigation strategies for controlling dust. Thank you.
Cool. Laylaa, are you ready?
I'm here. Can you hear me?
Maybe if you could speak a bit loud, I'm not sure.
Okay, how about now?
Sounds good to me.
Okay. Good afternoon, everyone. So I'm Laylaa, and today I will be presenting the project that I will be working on. So mining and mining activities offer a significant contribution towards air and environmental pollution. And this occurs through the dispersion of ore dust from mining areas, as well as through transportation, handling, and the storage of the mined ore from the mines to the storage facilities. The dispersion is assisted by climate factors such as wind or open transportation and storage of the ore, which results in elevated levels of metal dust, which subsequently has a negative impact on the environment and the surrounding communities. So this project involves monitoring the dispersion and exposure of dust from mining-related activities and the effects that this exposure has on human health. So over the years, contamination of the environment has been greatly improved due to the introduction of much stricter environmental guidelines. However, it has been found that inadvertent contamination from mining activities, such as transportation and storage of mined ore, has the potential to add significantly to the effects of the exposure. The iron ore handling facility in Saldanha Bay receives the iron ore from mines in the Northern Cape and stockpiles the iron ore for export. The ore is then stacked according to grade in stockpiles, which are exposed to the atmosphere, and then transported via a conveyor belt onto bulk carriers. Ore is also exported via the multi-purpose terminal, which involves transporting the ore in skips on trucks from stockpiles. Although this port was initially built with the export of iron ore, today various other metal ores such as lead, zinc, manganese, and copper are also exported. And figure 1 here indicates the terminal and the surrounding other mining-related businesses relative to the surrounding communities. So, as previously mentioned, the study involves monitoring the dispersion and exposure of dust from mining-related activities in the Saldanha Bay district and the health effects associated with this exposure. The research approach that will be undertaken for this project is to first map out the hotspot areas in the Saldanha Bay district using a GIS software. The sampling of the dust will be carried out using low-cost particulate sensors as well as gravimetric samplers. The dust samples will thereafter be analyzed to determine the elemental composition and concentration, and the results of the study will provide an indication of whether or not the mining-related activities are the sources of the elevated levels of air pollution, and whether these particles contribute to the deterioration of community health. So the main issue is the settling of the dust that is a risk to people in the surrounding communities of Saldanha Bay, Friedenberg, and Blue Water Bay, as the exposure of high concentration of metal dust results in various types of respiratory diseases. Some of the solutions that have been drawn at this stage is, should the dataset obtained indicate exceeded limits of metal concentration in the dust samples, re-evaluation of transportation of the ore needs to take place. The facility will also need to reconsider the methods of stockpiling the ore, but also this project provides an opportunity to reassess the current management practices to maximize both environmental and human health protection. Thank you.
Okay, thank you so much for those presentations. We have a question from Jochen. Could Waal kindly clarify the concept of water volume in tailings storage facility? Is that water retained in the solid matrix, or is he referring to decant water ponds?
Yeah, so in this case, it's more along the lines of the decant water. So I can go into the details if you want, but it's imagining that there is a body of water on top of the tailings, which is being drawn from to supplement the process water. But of course, based on large rainfall events or lack of rainfall events, this volume of water is going to vary, of course, and it will have an influence on the pore water as well. As it's larger volume in contact with the tailings will change the moisture content, but in this case it's more along the lines of the decant water. Yeah.
Okay, thank you. Are there other questions from the group?
This is Harold Anagon. Is it appropriate for me to come in?
Yes, thank you.
There's two brief comments on Laylaa's presentation concerning Saldanha Bay. In my experience of working in that area, the major dust episodes are associated with the transferring of ore into the ship holds during the drop from the conveyor belts into the hold if there are southwesterly winds blowing. So if you could add to her options of light bulb moments, that the control of dust emissions during ore transfer into the ships as the major source. Once the stock material is in the stockpiles and with the current mitigation measures, the static ore piles are relatively minor sources compared with the dust emissions associated with active process such as transfer into the ship holds and loading and unloading from stockpiles and the tippling of trucks. The second comment is of a more general nature and is a particular obsession of mine with the use of the term hotspots. It is a colloquial term. It is generally poorly defined and meaningless and should be totally banned from scientific writing and scientific discourse. We all know what it means colloquially, but it is often used as a shorthand and emotive term instead of being using proper scientific language to define a strong source of particulates or well-defined geographic cluster of sources. So please just avoid the use of that poorly defined term in any technical or scientific discourse. Thank you.
Okay, Laylaa, do you want to respond?
Yes, thank you, Harold. I will definitely take that into account with regards to the movement of the ore into the ships as the major source. Also, thank you for the hotspot as well.
Could I come in again? The low quality dust sensors, could you tell us the principle on which those units are operating? And then I'd like to, depending on what units you're using, I may offer a comment. Over.
So my project is still in the beginning stages, so I haven't yet decided which particular sensors I would be using to collect the dust samples. I'm currently so busy with my research proposal. So once I get a bit more into my research approach, then I would do more research based on which types of particulate sensors I would be able to use.
Right. I'm all in favor of using low quality sensors to be able to measure at multiple locations. I'm glad you've got a gravimetric sampler, which you are getting a physical sample to take back to the laboratory for analysis, because being at a coastal location, the big confounding factor is sea salt, that all optical based devices will also be recording particles of sea salt, which could be confounded with the mineral dust particles. So concurrent measuring of the meteorological wind speed and direction is a very powerful separator, which will help you to distinguish sea salt from mineral dust, depending on the location and your multiple sites. Downwind and not downwind of the terminal will help you to discriminate those. The major environmental effect of the dust is in fact not with the suspended particles, but what we call the impacted particles that cause the red dust on the vertical surfaces of buildings and structures and plants in the area. And offline, I will, if you wish, discuss with you an alternative sampler, the multi-directional sticky pad sampler, which is capable of measuring a horizontal flux of discoloring dust as opposed to the suspended dust, which will be sampled by your gravimetric sampler. Over.
Thank you, Harold. Yes, I would really appreciate it if you could shed more light on that offline. Thanks.
Hi, Harold. Just maybe if I can come in, I see that Yura is not actually online. I must just check that she's actually getting these invites. But, you know, she's doing work on some sort of low cost, I would say more low cost than low quality, personal monitors. And so we're going to look at sort of mounting some of these along with your gravimetric samplers and then your normal monitors. So to try and get some kind of indication of what these different monitors are picking up or able to pick up, so we can compare the different data and also use them in a complementary manner.
I think we have one question for CK, right? There's one at the bottom here. No. I can read it out to you if you would like.
Yes, please, go for it.
Sure. It says, can you please clearly identify what you mean by different kinds of coal dust? Are you looking at pit, lignite, bituminous, or anthracite differently? And will you be focusing on one type of coal, for example, bituminous coal?
Hi, thank you, Matthew, for your question. I mean different kinds of coal dust in terms of their mineralogical content. In terms of my study, I'm looking at one rank of coal for now, which is bituminous coal. So I think the clear answer would just be different types of coal based on their mineralogical and physical characteristics when they are turned into dust. So their size and their shape and all those kinds of characteristics that separate them. I see you've got another question there. In terms of PSD, will she focus on size fraction, say PM 2.5? So right now, with the way that we have designed getting the dust, we're looking at the -10 fraction. We haven't necessarily found a way to get a size segregated -2.5 fraction in terms of microns for when we say PM 2.5, we mean particles less than 2.5 microns in size, just to clarify for everyone. So yeah, we're looking at PM 10.
And I maybe also just come in on that point is that we will be looking at generating dust from these fine coal samples. So using, for instance, a pie swirl, we've kind of been trying to source, they're rather expensive. We wanted to try and put in an application to buy one, but we have got access to one actually from Oxford University, who are partners with us in the mine dust work. So we're probably going to generate our own PM 2.5 dust. The whole thing is we won't be working on, as CK said, this project's working more on the characteristics of coal than actual coal dust that is collected at sites.
Okay. If anyone else has a question, it might be, and if you're willing to come forward and maybe open the video as well. Otherwise.
Well, sorry, I missed the opening presentation. What was the topic of the first presentation, please?
You can ask Agnes. I don't know if I'm going to misrepresent her here, but she's looking at using isotope studies to identify potential different sources of sulfate in ARD. I think it's more than just sulfate, but her presentation focused on sulfate in this case. So tracking whether the sulfate is coming from either the mine workings or from atmospheric sources or fertilizer potentially, or other, sort of trying to understand the generation of acid mine drainage from an isotopic perspective. But I don't know if I answered you well there, Agnes.
Yeah, so you are right. It's a little bit more than just sulfur, because what we are planning to do is to measure both the sulfur and the oxygen isotope composition of the dissolved sulfate, because the sulfur isotope composition will indicate the source of the sulfur in the mining area that can come from mining activities, so directly from the pyrite, or atmospheric sulfur deposition fertilizers. It also refers to different physicochemical and microbiological processes that are operating in the mining area and controlling the mobility of the dissolved sulfate. And secondly, the oxygen isotope composition can show us that which mechanism is the dominant one during the oxidation of pyrite. So the oxidation is happening via the molecular oxygen or biologically mediated oxidation is the dominant one via the oxidant Fe3+. And we are trying to make a model that how is the acid rock formation happening and what's happening with the sulfate in the mining environment after the generation of the pollution.
Agnes, may I ask if you are dealing with, when you're talking about mining environment, are you talking about coal mines or gold mines or mining in general?
Yeah, so we are focusing on a coal mine in Mpumalanga, but of course the technique can apply for every type of mine. Yeah, and also just if I can make a quick comment on your previous comment to Laylaa. Isotopes can be used to make difference between the mine dust and also the particles that are coming from the ocean as well. So because these two things have different isotopic compositions, so this allows the differentiation between the particles from these two different origins. Just if Laylaa would be interested in some isotope research in the future.
Okay, if I may add something. I see from your surname, Agnes, that you may not be of South African nationality born. Just in relation to your wishing to distinguish between fertilizer-derived sulfur and mine-related sulfur, a little bit of industrial espionage is that the fertilizers in South Africa are produced by Omnia Fertilizer, which is a byproduct of the Sasolburg operation, so that the sulfur in the fertilizer is likely to have the same or similar isotopic composition to the Witbank coal fields, because the sulfur is also a derived or secondary product from the coal to oil conversion process. So it might not be as discriminatory. Similarly, the atmospheric deposition from Eskom and Sasol power stations is also derived from the same coal. So the similarities might not be as stark as one hoped, that obviously are the intermediate temperature processes which might cause fractionation of the different isotopes, which is your signal. but they are almost all in some way derived from coal. Over.
Thank you very much for this comment. Actually, it's very useful to hear, but I think that because usually fertilizers, so I know that in Europe, the fertilizers has positive sulfur isotopic composition, whereas most of the pyrite has negative. So I think that during the processing, because there are different reactions, these reactions induce the fractionation of the isotopes, so somewhat that should change the isotopic composition of the original material. But unfortunately, I still haven't found any literature in South Africa that somebody ever measured the isotopic composition. If you know, you are aware of any type of research in connection with this, please share it with me. I would be very happy to read something about that.
Okay, I will look out. The one name that you might look up in your literature is from the University of Virginia in Charlottesville, Steve Macko. Steve Macko, M-A-C-K-O, the isotope specialist whose work might be useful for you to add additional discriminators based on combined isotope and chemical subcomposition of particles from different sources. Over.
Cool. I think for the last little while, we might try quickly. Initially, this whole session is supposed to have happened at the Minerals to Metals Research Day, and of course, the format and all would have been somewhat different. Initially, the idea was that we'd open up the floor to address a particular challenge question for every session. For us, the gist of it was that the overarching theme, or let's say the umbrella which overlies all of our research is around how we are using different assessment methods to try and produce information that, diagnostic information of various kinds, or monitoring systems and so on. But at the end of the day, these systems might not necessarily direct you to a solution. So the kind of question there is that you can potentially assess many things, but not necessarily get to an obvious solution. So that was the challenge question, as it were. Personally, my opinion on that, oh right, Aisha wants me to put my video on. Hello. So personally, the way that I look at this is that if you turn it around and you ask yourself, I'm trying to understand whether solution A or solution B is going to be the solution that I want, or intervention A or intervention B. Ultimately, we are dependent on some kind of parameters or indicators, or some sort of information ultimately that we need to inform our decision, right? So we make use of, on a financial basis, people look at things like the NPV of a project, or the rate of return, and all of these things. They try and produce some diagnostic information to say that this is how this option is behaving. And so, but the solutions that we're having today might not always be the right solutions. So we know that we still have many problems associated with acid rock drainage, associated with mining water management, associated with dust in various forms. And so I think the main goal of this kind of research often is to try and come up with new assessment methods that will produce new kinds of information or new insights, or at least do it in a slightly different way that may allow us to improve our decision making, improve our monitoring capabilities, and ultimately lead to new kinds of solutions. I think that's my take on it, at least. I don't know if there's take up from the rest of us.
Harold, you've got your hand up. Do you want to?
Yes. Along the lines that Siobhan has indicated, one of the big outstanding or health and environmental problems associated with dust and mining is related to the relative toxicity of quartz silica. We know that the composition of the gold mine tailings of the Free State and Witwatersrand comprise upward of 80% of the mass of the material is quartz silica. However, there is no specific air quality standard for silica quartz in the ambient environment. There is, of course, the OSHA industrial health limit, but as you are mostly aware, or let me make you aware, that the industrial health limits explicitly state that these values for industrial exposure should not be used as a basis for deriving ambient air quality guidelines. As is nevertheless often done, you say take the industrial limit and divide it by 50 or divide it by 100 and say that's an appropriate limit for public exposure. It is scientifically unsound, totally invalid, and no better than a thumbsuck to take an industrial hygiene standard, which is a completely separate beast, and try and by an arbitrary factor change that into an environmental factor. So those of you, and I mentioned in relation to Laylaa's was work on the previous speaker on the biological response in vitro to the coal particles. We need to find an appropriate air quality standard for silica quartz in the ambient environment by determining, is it in fact more toxic, and if so, more so toxic than the general PM10, PM2.5 standard. Because at the moment there's a lot of public concern, anecdotal evidence of people who are falling ill and to all sorts of diseases, cancer and HIV/AIDS and tuberculosis and diabetes related to exposure to dust. Some of them are credible, others are implausible, but the answer is there's no good information on ambient exposure and its health outcomes, and in vitro experimentation would be one sound way, as the Waal has indicated, to start establishing fact from fiction in this important mining sector for South Africa.
Okay, I think we have time for one more question. Is there anyone that has anything burning to say? Jen?
I'd just like to say thank you, Harold, for that. I absolutely agree with you 100%, and I think that this is coal. Actually, we seem to end up doing so much work on coal, even though I think coal mining itself is, is going to be phased out, or hopefully will be in the future. But yet, as much as we don't understand silica, we understand even less about silica in coal. So the coal matrix makes it so much more complicated and so much more urgent that we understand this. And all this anecdotal sort of evidence around health issues due to exposure to coal, we just don't have enough scientific evidence. So I think that's really very valid comments that you made there, Harold. And I think one of my takeaways from working in this place and in this space, and just listening to the conversations and the presentations today, definitely it's this issue of that that you can't use one tool to understand these sort of complex interrelated impacts associated with water and dust, that we need to use combinations of tools. And I think more and more of our work sort of takes us down that kind of road of using combinations of different indicators and tools to understand impacts, and to understand how these, and to be able to use these tools in a complementary way. Thanks.
Is there any last comments from the speakers?
Well, okay, I guess I can chip in quickly. I think, of course, in the very limited time that we have to show a little bit of our projects, I think all of us know we're only scratching the surface, or either giving a broad overview and not digging into the details, or the other way around, giving only a slice and not showing the breadth. But as Jenny says, it really will come down to the kind of the suite of indicators and the suite of tools that you use to try and understand these problems. So yeah, I suppose this is not necessarily the right forum for it yet, but of course at some point each of us is going to give a nice presentation where we show our wonderful results and show how they all tie together and give some great insights into each of the problems we're looking at. But this is, I suppose, just to tantalize a little bit. Yeah.
Okay, thank you so much. I think if there isn't anyone that pops up now, with any questions, we can call it a day. I'd like to thank all the speakers for coming through and presenting their work, and for those who commented and asked questions. I hope it's been a fruitful discussion for all. Okay.
Thank you, Aisha.
Thanks, Aisha, and for everyone who presented. Great session. Thank you.
Thank you all for attending. Hope we'll see you again next week.
I will send through a recording of the session when it's made available.